Go through these properties and make sure that you understand the meaning of these. Well, here I have illustrated the meaning of density of electric field. If you look at charge A, there are only very few lines of force starting from there. Charge B has a lot more. Charge C has large number of lines of force or field lines starting from there. Tell me, using property number 4, which of these contains the largest charge? A, B or C? Property number 4 is the number of field lines originating or terminating at a charge is proportional to the magnitude of the charge. You can see from A only very few lines originate, whereas from C large number of lines originate. That means C is a much bigger charge than A. And also look at the density of the field lines. The density of the field lines is much greater around C than around B, and is much greater than around A. The density of the field lines indicate what? The strength of the electric field. So if you take a point here, the strength of the electric field here will be much greater than the strength of the electric field here, will be much greater than the strength of the electric field there. Alright? Okay. Let's now talk about yet another important concept. Electric flux. What is the meaning of a flux? Flux is really something that flows, is that right? Flows across something. Flux. Alright. The intensity of an electric field can be defined using the concept of lines of force that we have already done. The intensity of electric field E at a point in an electric field is defined as the number of lines of force crossing at right angles to a unit area containing that point. Suppose we have some lines of force coming from one end of the room and crossing this area. You see, if I want to find the electric field at this point, what I'm going to do is I keep an area of 1 square meter containing that point and measure the number of lines of force crossing that area. In other words, the number of lines of force crossing per unit area containing that point is a measure of the electric field at that point. You can see we are coming on to discussing the concept of flux. Now here you can see lines of force moving from left to right and crossing this area. Right? Now what is the definition of electric field I gave you? If I want to define the electric field here, all I need to do is measure the number of lines of force crossing at right angles to a unit area placed there. In other words, number of lines of force crossing at right angles to a unit area containing that point is a measure of the electric field at that point. And here is another illustration of electric field lines crossing a given area. Alright? I hope you got a concept of what it means, electric field lines crossing a given area. Well, the number of lines of force crossing at right angles to any given area is called the flux crossing that area. The flux crossing that area. So, if I have a total area A here, the number of lines of force crossing that whole of that area is called the flux crossing that area. You see, what did we say the electric field is? Electric field is the number of lines of force crossing unit area containing that point. But flux is the total measure of the lines of force crossing the entire area. And so we can use the concept of flux to define intensity of electric field. A flux is a measure of the total number of force crossing the entire area. If you divide that flux by this area, I will get the flux per unit area, and that will be a measure of the electric field. Alright, we will represent the electric flux by the Greek letter phi. Alright, so the electric field E is then the flux per unit area. In other words, E equal to phi over A. I want you to look at this carefully and learn it. We are going to use it in the next lesson. So you must be very well thorough with this. What is the definition of electric field using the concept of electric flux? E is flux per unit area. Flux is a measure of the total number of lines of force crossing at right angles to a given area. An electric field is flux per unit area, number of lines of force crossing at right angles to a unit area. So electric field intensity is flux per unit area. Therefore, flux, the total flux will be electric field multiplied by the area, and that is measured in Newton meter squared per coulomb. Phi, electric flux crossing a given area, will be E times A, where E is the flux per unit area. So flux per unit area multiplied by the area will be the total flux crossing that area. Alright, let's have a look at the concept of flux one more time. Here is an illustration of an electric flux. If you notice, there's a large number of lines of force going from left to right and crossing an area. This is a side view of, in other words, the area is kept like this. And now if you look at it from the front, this is what you see. Each of these dots is a line crossing. Now what happens if I tilt the side? You can see the flux is going to be less, because remember, flux is a measure of the lines of force crossing the area, the normal lines of force. In other words, we should consider the lines of force at right angles to the surface. Now, see what happens to the flux when I change the angle of the plane. Now, as the angle of plane is changed, you can see the flux is becoming now less. The number of lines of force crossing at right angles become less as the surface is now inclined to the lines of force. You can see as the angle, if I incline it more and more, the flux will become very small. And finally, what will be the flux to that surface when the surface is parallel to the lines of force? There will be no flux. That means I can increase the flux through a surface by making the surface more and more at right angles. And the maximum flux crosses the area when the area is at right angles to the surface. It's very important to understand that. We will now look at electric field due to a system of charges. In other words, if I have more than one charge placed in a region, electric field at any given point will be the vector sum of the field produced by each of these charges. Is that right? Electric field is a vector quantity. So what will the field look like if you have a system of charges? If a region contains more than one point charge, the field at any point is the vector sum of the field due to each of the charges in that system. Alright, consider two positive point charges as here. A is a positive charge, B also is a positive charge. That means if you take, say, this point where I'm pointing. Now, at this point, there will be a field due to A, I'm going to call it E sub A, and there will be a field produced by B, I call it E sub B. And each of these fields is represented by an arrow. Now tell me, why is the blue arrow E sub A smaller than the green arrow E sub B? Well, because B is closer to this point, that means the intensity of the field is greater at this point due to B than due to A. A is farther away, so the field at this point due to A will be small, and the strength of the field at this point due to B will be larger, and the net field at this point will be the sum of these two. Now, you know how to add vectors, is that right? You can actually draw a parallelogram with these as the two sides, and the diagonal will then give the resultant. That means the resultant field will be therefore this. The resultant field in here will be that. So every point there will be two electric fields, one due to A and one due to B, and the net electric field at any point is the vector sum of these two. Alright. You can construct some of those in there. Now there are two field vectors at every point. The field at each point is the resultant, which is the vector sum of these two. For example, the field here, this is the resultant. I'm sure you understand why that is a resultant. Here, that is the resultant. And here, this is EB, this is EA, therefore that is the resultant. And here, EA and EB both are in the same direction. And look at the resultant field there, they can simply add up. Alright, let's now draw the net field due to two positive point charges. If you now draw, rather than drawing them individually, if you draw the net field, how will it look like? Look at this. The field due to two positive charges will look like this. A positive test charge placed here will move away. Well, it wants to move away from both charges. That means the field due to the two system will look like this. The field lines will be diverging from both. Why is this space in between? What is the specialty there? You can see the field due to the first charge is equal and opposite to the field due to the second charge. There will be no field in between. Right? How about the specialty here? The field lines are almost parallel. What does that mean? If the field lines are parallel, it tells you the field in that region is almost uniform. Field is not changing. So you must be familiar with these kind of drawing field lines. Now tell me, if this represents the electric field lines due to two positive charges, what will be the field due to two negative charges? Can you try and construct one on your own? Try before I go to the next slide. So there is a point between the two charges where the net field is 0. Okay, field lines due to two negative charges. Well, this time I'm going to